Hi, I hope that you are doing great. In this video, I'm going to solve the problems related to Lecture 1 on linear algebra and geometry. If you're following my YouTube channel, you probably know that there is a playlist on my YouTube channel called Linear Algebra and Geometry. This video is uploaded onto that playlist. In the descriptions below the video, you will find 5 links. The first link gives you access to the PDF file containing the problems that I am going to solve in this video. The second link is the link to the PDF file of these notes that right now you see on your display. And in this lecture, I will write down my explanations and solutions in between the empty spaces that I have already provided in this file. In this file, the solutions to problems that I will present in this video are not included. I use iPad Pro together with Apple Pencil and GoodNotes 5 application to produce these videos. The content of the third link is exactly the same as the second one, except that this one is on the GoodNotes file. I strongly recommend you to have one of these files available when watching the video. I think having the notes in front of you while watching the video could be very helpful in active learning. The fourth and fifth links are links to PDF and GoodNotes file accordingly of these lecture notes, but this time they contain all my solutions to the problems. I spent many hours enthusiastically to make these videos available for free. If you found the video somehow helpful and enjoyed watching it, I would be grateful if you could give me a thumb up. And by subscribing to my channel, you not only support me, but you will be immediately notified if I upload a new video. Okay, so now let us start solving the problems. The first problem. Determine each of the following determinants and simplify the results as much as possible. So all of them are 2 by 2, both of them are 2 by 2 determinants, so I have to use the definition of a 2 by 2 determinant to calculate these determinants and then finally simplify it. So I would say number 1, so if I want to calculate this, I need to multiply these two numbers together. I need to multiply these two numbers together and then subtract them. Okay, so if I do the first one, a plus b times a plus b is a plus b to the 2, and then a minus b is a minus b to the 2. Yes, and then I can use the quadratic rule to expand them, so it becomes a squared plus 2ab plus b squared, and then I will have minus a squared minus 2ab plus b squared. And then I remove the unnecessary brackets, so then it becomes 2ab plus b squared minus a squared plus 2ab and minus b squared. Yes, and then you see that this a squared here and this negative 1 cancel, b squared and b squared are cancelled, so I will get 2ab plus 2ab. So that is the final answer to this determinant. As simple as that. So let us go to number 2. So number 2, I do the same thing. I need to multiply these two, and then I need to multiply these two, and then subtract them. So then it becomes equal to sine of alpha plus sine of beta times sine alpha minus sine beta, and then I have minus cosine of beta plus cosine of alpha multiplied by cosine of beta minus cosine of alpha. Yes, and I have to simplify that, and immediately you realize that these two are actually conjugate pattern. This emerges the conjugate pattern. This is also conjugate pattern. So what I can do, I can write the first one to the 2 minus the second one to the 2 minus the second one is also a conjugate pattern, so it becomes cosine to the 2 minus cosine to the 2 beta and alpha. Yes, and then I remove these unnecessary bracket, so sine squared alpha minus sine squared beta minus cosine squared beta plus cosine squared alpha. Yes, so then I can combine these two together. Sine squared alpha plus cosine squared alpha is a famous trigonometric identity, and then I can factor a negative sign out between these two terms. I will factor a negative sign out and I will have sine squared beta plus cosine squared beta. Yes, and then you know that based on the trigonometry, this is 1, this is also 1, so the answer would be 1 minus 1, which is 0. Now, second problem. Let a, b, and c be real numbers such that the a plus b plus c equals to 0. Determine the following determinant. Yes. Okay, so here I would prefer to use the Sarris mnemonic. Yes. So what can I do? I can just rewrite this in this form. So I will have A, B, and C, and then I will have B, C, and A, and then I have C, A, and B. Then I will repeat the first two columns, A, B, C, B, C, A. And then I can follow this rule, yes. So I can, for example, I will consider these, and these. So I multiply them. The product of the first one becomes ABC. I will not change the sign. The second one is also ABC. You see, I am multiplying these A, B, A, C, B, which becomes ABC, the same one ABC, and the same one ABC. So then it also becomes ABC. But then this time when I multiply them, so let me change my color. Now I multiply these, it gives me b to the 3, but I don't write b to the 3, I write negative b to the 3. And then I multiply these, it will give me negative a to the 3. Yes, and then it will give me negative c to the 3. And then what I need to do to calculate the determinant finally, I need to add all these numbers here. I have 3abc minus a3 minus b3 minus c3. So it becomes 3abc. So the question mark, if this is my question mark, this is equal to 3abc minus a to the 3 minus b to the 3 minus c to the 3. But now I can simplify this. I have given a plus b plus c is equal to 0. For example, I can write c is equal to minus a minus b, and then everywhere that I see here in this question mark, I can replace it with minus a minus b. Yes, so let us see what happens. So then it becomes equal to 3ab. Instead of c, I put minus a minus b, and then I have minus a to the 3 minus b to the 3. Then I will have minus a minus b to the 3. I will try to simplify this expression. So I will multiply 3ab inside, so it becomes minus 3a squared b minus 3ab squared. Yes. And then I have minus a to the 3 minus b to the 3. Because this power is odd, so I can factor a minus sign out. This minus sign will actually turn this one to a positive sign. So it becomes positive a plus b to the 3. And then that's also a famous identity. Yes, it's minus 3a squared b minus 3ab squared minus a to the 3 minus b to the 3. Then I will expand this expression using the Newton's binomial theorem or the very famous simple formula. If I want to raise a binomial to power 3, the answer is the first one to the 3 times the first one to the 2 times the second one, 3 times the first one times the second one to the 2, and finally b to the 3. And then interestingly, you see that everything is now cancelled. This is cancelled with that one, positive and negative, positive and negative, positive and negative. So nothing is actually left, which is 0. Okay, now let us look at this problem. Is there any natural number n such that this n by n determinant becomes equal to square root of 2, motivate your answer. So here I am looking, if possible, for a natural number n. Yes, of course, if n is natural, then you see that all these entries that you see inside this determinant are all rational numbers. Yes, and then the determinant, if I want to use the definition to expand and calculate this determinant becomes a sum over all possible signed elementary products consisting of the entries of this determinant. So if I want to write a definition, it is the sum of these expressions, yes, a1j1, a2j2 up to a n j n. Yes, so this thing that you see here is the formula for calculating this determinant, and here each one of these factors that you can see here are elements coming from this n by n determinant. Okay, but all of these numbers are are rational numbers. So it means that this elementary product, which one it is, it doesn't matter, all of them are rationals. And if I multiply them by a plus or minus sign, it remains rational. And I am adding all these signed elementary products together. Each elementary signed product is a rational number, so the sum is also a rational number. But on the other hand, square root of 2 is an irrational number, and it is not possible to have a rational number equal to an irrational number. So the answer to this question is there any natural number n for this to happen? The answer is no, and that's the motivation, because the left hand side is always a rational number, the right hand side is an irrational number, and they cannot be equal. Okay, let us solve the next problem. Solve each equation for x. There is not needed here. Okay, so if I want to solve the first equation, that is a 2 by 2 determinant, so I do this. I can expand this determinant, which is a 2 by 2 determinant, so it becomes x minus 1 times x plus 1 minus the product of these two numbers, which is 5x, is supposed to be equal to 5. And then what happens, I use the conjugate rule to expand this, so it becomes x squared minus x, then I have minus 5x equals to 5. So that's a quadratic equation, yeah, so it becomes x squared minus 5x minus 6 equals to 0. You can either use the PQ formula or ABC formula to solve this, but it would be very easy if I use factorizing the polynomial here. Yes, I put an x here and another x here, and I ask myself, I need two numbers whose sum is equal to minus 5 and the product is minus 6. And it is very clear that one of those numbers is minus 6, the other one is positive 1. So you see that if I add them, it becomes minus 5, and if I multiply them, it becomes minus 6. And then by the zero product rule, the product of two numbers is 0, so this means that either the first one is 0 or the second one is 0. But then this means that either x is equal to 6 or x is equal to minus 1. So these are the possible answers for the first determinant equation. Okay, so what happens for the second one? For the second one, I have a 3 by 3 determinant. I have to equate it equal to 0. But if you, before starting using, I don't know, the Sarris method or any expansion method for the determinant, it's better to see that immediately it becomes clear that this is an upper triangular matrix. Why? Because if you look at the diagonal, every entry below the diagonal is 0. So everything here is 0 below this. So this is an upper triangular matrix, and the determinant of an upper triangular matrix, we had it in the lecture itself, it's equal to the product of the main diagonal entries. So then if I want to solve that one, this implies that x plus 2, 3 minus 2x multiplied by x squared minus 1. What I have written here is the expression for this determinant, but now I have to equate it equal to 0. Yes? So then what happens is that, again, the zero product rule, this implies that x plus 2 is equal to 0, or 3 minus 2x is equal to 0, or x squared minus 1 equals to 0. So the first one gives me x is equal to minus 2, or the second one gives me x is equal to 3 over 2, and finally the last one gives me x is equal to plus or minus 1. Okay, now let us go to the next problem. Problem E. Show that the matrices commute if and only if that this determinant is equal to 0. Okay? And this is the problem 34 on page 183 of the course book. Okay, so let me call, for example, this one matrix A, and then let me call this one matrix B. Yes? Then what can I say? I would say that A and B commute if and only if. What is the meaning of these two matrices commute? It means that B times A is equal to A times B. Yes, and then what this is equivalent, you see I am just writing the double-sided arrows all the time. Instead of B, I put its matrix D, E, 0, F multiplied by A, which is A, B, C, 0, C. This is supposed to be equal to the other way around. So this multiplied by D, E, 0, and F. Okay, and this is also equivalent to I start multiplying the matrices. For example, I partition the left matrix to the row to its rows, and the right matrix to its column, and then I will multiply each row by each column here. Yes. So, okay, I just multiply it. It becomes DE. So I need to multiply D by A. So I have to multiply D by A, and then E by 0. So D by A, E by 0, and add them. So it becomes DA. And the next one becomes DB plus EC. And the next one is 0 times A plus 0 times F, which is 0. And then 0 times B plus F times C. Yes, this is equal to. And then I multiply the right hand side. It becomes AD. And then the next one becomes AE plus BF. And the next one is again 0. And then I will have finally CF. So this happens if and only if. Let us look at here. So 0 is already equal to 0. FC is already equal to CF. And DA is already equal to AD. So this happens if and only if what is left here is equal to that one. So it means that DB plus EC equals to AE plus BF. Yes. And now I can move everything to the left hand side. So this itself is equivalent to saying that DB minus, so let me write EC minus AE minus BF is equal to 0. Then I can take this one with that one to factor B out, and I can take these two to factor E out. Yes, so what happens? This is also equivalent to saying that B times D minus F, and then on the other one I have let me factor minus E out. The reason is that I want to have A minus C. Yes, by looking here I see that the combination that I have is D minus F and then A minus C. You see, so this motivated me to factor minus E out instead of factoring only E out. Yes, and then it is completely clear that is the definition of that determinant. Yes, this one can be written as BE, and then I can write A minus C D minus F, and on the right hand side I have 0. Yes, so this is 0. Why this is correct? Let us check. If I ask you what is the definition of this determinant, you would say that this is B times this expression, which is the first one, minus, and then this expression multiplied by that, which is exactly this one. So we started from here, A and B commute, if and only if all the time, yes, all of them are double-sided arrows, and then finally I reach to this final step. So it means that these two statements are actually equivalent. So this happens if and only if this happens. Yes. Okay, now we solve the next problem. Problem F. Show that the determinant of A is a 2 by 2 matrix, is equal to 1/2 the determinant of this matrix, where trace of A is the sum of the entries on the main diagonal, as you already know. Okay, so we want to prove this. And I have forgotten to write, this is also a problem from the course book. It's problem 36 on page 183 of the course book. Okay, so if you want to solve this problem, we can consider a generic matrix 2 by 2 matrix. So let A be this matrix, A, B, C, and D. Okay, so what I need to calculate, I need to calculate the trace of A here and here, and trace of A squared. So the trace of A is very clear. So trace of A becomes A plus D. Yes. And for calculating trace of A squared, first I need to calculate A squared. So it means that I have to multiply this matrix by itself. And if you do this matrix multiplication, it becomes A squared plus BC, A B plus BD, and then you have AC plus DC, and finally you have BC plus D squared. Okay? So then it means that the trace of A squared is equal to the sum of the entries on the main diagonal of A squared. So this becomes A squared plus BC plus BC plus D squared. So if I write it, it becomes A squared plus 2BC plus D squared. So that would be the trace of A squared then. Yes, so this is the trace of A squared. And now everything is ready to calculate the right hand side of this expression. So I would write the right hand side is equal to 1/2 the determinant of trace of A. Trace of A is A plus D, so I put A plus D here and here. And then I have 1 here, and instead of trace of A squared, I put this expression that I got just right now. So this is A squared plus 2BC plus D squared. And now I calculate this determinant, okay? So for calculating this determinant, I have to multiply these two. I have to multiply these two and subtract them. Then I have a factor of 1/2 here as well. So then it becomes 1/2. Then it becomes A plus D times A plus D, which is A plus D to the 2, minus A squared plus 2BC plus D squared. And then I expand and simplify this expression, yes? So this becomes 1/2. Then I use the quadratic rule, the first one to the 2 times the first one times the second one to the 2. And then I apply the minus sign inside the bracket. So it becomes negative A squared minus 2BC minus D squared. And then you see that this A squared and that one are cancelled. This one and this one is also cancelled. So then I have 1/2, and I can factor a 2 out, yes? it becomes AD minus BC. But then I can simplify these twos and then I will get AD minus BC. Yes, but AD minus BC is exactly the determinant of this matrix A times D minus B times C. So what I get, this is exactly equal to the determinant of A, and this is the left-hand side. Okay, so we were able to prove that the right-hand side is equal to the left-hand side. Okay, so this problem, we have a 3 by 3 matrix A, and we're supposed to calculate the determinant of this combination here. We don't have any formula that relates the determinant of some of the two matrices to the determinants of each matrix individually. So what we can do here is just to calculate A transpose and A transpose A, add them together to get a new 3 by 3 matrix, and use one of the methods for calculating that determinant, 3 by 3 determinants. Okay, so what I want to do is actually I will follow exactly the same strategy. I will multiply A by A transpose first. So A is just this matrix 1, 2, and 1, 0, 0, and 1, 1, 0, and 1. I multiply it by the transpose. So to write the transpose, whatever I have for a row, I put for the corresponding column. So this is the first row, I put it as the first column. So it becomes 1, 2, and 1. Then I have 0, 0, 1 as the second row, I put it as the second column, and the next thing exactly the same. And then I multiply these two matrices. So if I multiply these two matrices, it becomes 6. So yes, because 1 should be multiplied by 1, 2 should be multiplied by 2, and 1 should be multiplied by 1, and then I add the results. If I do that, it becomes 6. Yes. And then the next one becomes 1, the next one becomes 2, the next one is 1, and 1, and 1, and then I will have 2, 1, and 2. So this is A transpose. Now I calculate A transpose A. To calculate A transpose A, I write the A transpose first, which is this matrix, as we did before. And then I multiply it by the matrix itself. We have to do this because we know that in general two matrices do not commute when we multiply them. So we have to do it once more. So then this becomes 2, then I will have 2 here and 2 here as well. 2 here, 4 and 2, 2, 2 and 3. Yes? Now I need to add them. So A transpose plus A transpose A becomes a new 3 by 3 determinant. So I add the entries correspondingly. So for example, 6 plus 2 will give me 8, and then this next one is 3, the next one is 4, 3, 5, 3, 4, 3, and finally 5. Yes? Now I want to calculate the determinant of this new matrix. So let me use the Sarris rule. So I would write 8 and 3 and 4 and 5, 3, 5 and 3, 4, 3 and 5. Then I will repeat two columns, the first two columns here, 8, 3 and 4, 3 and 5 and 3. Then I need to multiply these entries, and these entries with the same signs. So it becomes 8 times 5 is 40 times 5 is 200. I keep the same sign. 3 times 3 times 4 is 36. I keep the same sign. And then again 36 here. But then I have to multiply the other ones in this direction. So the next, and then this one, and finally this one. Yes, if I multiply the first three numbers, 3 times 3 is 9 times 5 is 45, but I write minus 45. Yes. And the next one, 3 times 3 is 9. 9 times 8 is 72, but I would write minus 72. And then finally I have 20 times 4 is 80. I will write minus 80. Then I need to add them, so exactly in the same order. So what happens is that I will have 200 plus 36, 36, and minus 80, minus 72, minus 45. So for example, this 72 and this 72 are gone. So this is 120, and the answer becomes 75 at the end. Okay, so next problem. Prove that x1, y1, x2, y2, and x3, y3 are collinear points if and only if this determinant is equal to 0. This is problem P1 on page 184 of the course book. Okay, so of course this problem is interesting if all these points are distinct points, yes, so all of them are distinct. If you don't mind, let me first calculate this determinant and try to change the form of this condition to a normal condition not involving the determinant. So I will write it like this. So to calculate this determinant, I use the Sarris Rule. So I will have x1, x2, and x3, y1, y2, and y3, and then I have 1, 1, 1. Then I repeat the first two columns, x1, x2, and x3, y1, y2, and y3. And then I will multiply these, and then these three, and then these three. So the first one is x1, y2. The next one is x3, y1. And the next one is x2, y3, and then I will do the other way around. So I will have these three and these three and finally these three. So let me write them a little bit higher. So here I will have x2, y1, but I will change the sign. It becomes negative x2, y1, and the next one becomes x1, y3 with negative sign, and the next one becomes negative x3, y2. Yes. So then what happens for my determinant? So the determinant is equal to this. So I would write that the determinant of x1, x2, x3, y1, y2, y3, 1, 1, 1 equals to 0 if and only if this sum becomes equal to 0. Yes, so if and only if x1, y2 plus x3, y1 plus x2, y3 minus x3, y2 minus x1, y3 minus x2, y1 is equal to 0. And this is again if and only if. I simplified this a little bit. So I take these two terms together, the ones that have x1, and I factor x1 out, so it becomes y2 minus y3 times x1. Then I will take these two containing y1 and these two, and then I will factor y1 out, so then it becomes x3 minus x2 y1, and then finally I write these two terms in a pair of brackets. Okay, so I would consider this condition as a star. I give it a name, and what I'm trying to say is that this condition given in the problem based on this calculation is completely equivalent to this star relation. Yes. Okay, now we go now let me write it in this way. So now, motivated by this condition, I define an equation here. So now consider the equation y2 minus y3, but instead of x1 I put x, plus x3 minus x2 I put y, and then I have x2 y3 minus x3 y2 equals to 0. So consider this equation. Yes, what we know is that b and C, let me call this point B. So let me give them names. So let me call this point A, let me call this point B, and let me call this point C. All these points are supposed to be distinct points, yes? So I would say that B and C are distinct. Yes, so what does it mean? It means that either the x coordinates are not the same, or at least the y coordinates are not the same. This is not the case that both x coordinates and y coordinates are the same. So it means that here either x2 is not equal to x3 or y2 is not equal to y3. So this is important here. So x2 is not equal to x3 or y2 is not equal to y3. So it means that at least one of these conditions should hold. So then it means that this equation that you can see here, okay, if I consider this, look, for example, A, if I consider this B, and if I consider this C, then you will have this form. You will have AX plus BY plus C equals to 0. And you know that this coefficient and this coefficient are not simultaneously 0. Because either x2 is not equal to x3, it means b is not 0, or y2 is not equal to y3, it means that a is not equal to 0. So it means that the equation that I wrote here is an equation for a straight line because of these two conditions, because one of these conditions has to hold actually. Okay, so what I conclude here is that therefore this equation is an equation of a straight line. Call it L. Yes. So I gave this a name. So this one now is equation of a straight line. I call it L. Okay? But now my claim is that this line always passes through B and passes through C. Okay? So our claim is that L passes through both B and C. Okay, how proof of the claim? How can I prove this claim? So I want to show that this line L passes through point B. It means that the coordinates of the point B should satisfy the equation. Yes. So it means that if I replace x with the x coordinate of B, and if I replace y with the y coordinate of B, this should satisfy. This equality should be valid. So let us check. I replace the x coordinate by the x coordinate of the point B, but the x coordinate of the point B is x2. So okay, so I would write y2 minus y3 multiplied by x2, and then I will replace the y in the equation with the y coordinate of point B, which is y2, and then I will have x2 y3 minus x3 y2, and I want to check that is it true that this is equal to 0. Okay, so let us check. Okay, the left hand side becomes equal to, I just multiply that, it becomes x2 y2 minus x2 y3 plus x3 y2 minus x2 y2, and then I will have x2 y3 minus x3 y2. Yes, and if I continue, you immediately see that this x2 y2 and this negative 1 are cancelled, and minus x2 y3, positive x2 y3, and this one and that one, and it means that this is 0 and this is equal to the right hand side. Okay, for C it is similar. Similar, and you can check it yourself. So what you need to do is replace x with x coordinate of C x3, replace y with y coordinate of C y3, and then do the simple calculation, and you will see that this is always the case, that this line always passes through the points B and C. Okay, now what can I write? I can write this. I can write that B, C, and A are collinear if and only if what happens? B and C are already lying on L. So B, C, and A are collinear if and only if A lies on L as well. Yes? And this happens if and only if the coordinates of the point A satisfies the equation for the line L. So this happens if and only if y2 minus y3 times x1 plus x3 minus x2 times y1 plus x2 y3 minus x3 y2 is equal to 0. Okay, so we showed that B, C, and A are collinear if and only if this happens. Yes, and this happens if and only if this equation is satisfied. But look, this is exactly this star equation, and this star equation is all itself equivalent to this one. Okay, so I would say that instead of this last one, I can write if and only if this determinant of x1, x2, x3, y1, y2, y3, 1, 1, 1 is equal to 0. So now you can see that B, C, and A are collinear if and only if this determinant is equal to 0. Of course, in the future that we study the cross product of two vectors, there you will realize that this determinant is actually the absolute value of this determinant would be 2 times the area of a triangle with vertices A, B, and C. Okay? So then it means that, and I would say that A, B, and C are collinear if and only if the area of the triangle constructed on vertices A, B, and C is equal to 0. So then it means that these points are collinear if and only if this determinant is equal to 0. Okay, now let us start the last problem. What can you say about the 6 elementary products of this matrix defined in this way? Vector U multiplied by V transpose if U and V are column vectors in R3. Yes, so this is also a problem in the course book. I would say that this problem is simple for the case of vectors in R3. So let us consider the more general one, that the vectors are coming not from R3 but from R to some any power, to R to n for any n. Yes, so let me just modify the problem a little bit. So let V, U, and V be column vectors in Rn, yes, for any n. Okay, so what can we write? For example, the vector u, so let me write the vector. So the vector u has n components. I would call them u1, u2 up to un. And vector v has also n components, v1, v2 up to vn. Yes. But then my matrix A is defined to be the vector u multiplied by the vector v transpose. Yes, so then it means that I need to write this in this form u1, u2 up to un multiplied by the transpose of v, yes, which is v1, v2, v1, v2 up to vn. Okay, and then I need to multiply them. So if I am interested, of course, if you multiply them, it's clear. So it becomes u1 multiplied by v1, u1 multiplied by v2, and you continue u1 multiplied by vn, and then you have u2 multiplied by v1, u2 multiplied by v2, and then you have u2 multiplied by vn, and finally, if you continue, you will have un multiplied by v1, un multiplied by v2, and you continue write un multiplied by vn finally. Okay, so this would be your matrix. Okay, so what does it mean? It means that the entry on the so let me call it in this form. Yeah, the entry on the i's row and j's column of matrix A is actually ui multiplied by vj. Yes, so in principle, if I denote it by little a ij, this becomes ui vj, yes, for I and j from 1 to up to n. Yes, this is clear. But now assume that you want to calculate the determinant of a. So the determinant of a would be a sum over signed elementary products. But of course here we are not considering the signed elementary products, we are only considering the elementary products themselves. So it is a1 j1, a2 j2 up to an jn, in which j1 j2 jn is a permutation of 1 2 up to n. So they are the same numbers but probably in different orders. Okay, so let us consider this typical elementary product. So what happens? So a1 j1, a2 j2 up to an jn is equal to, instead of a1 j1, I can use this. You see, a sub ij is equal to ui times v sub j. So it means that a1 j1 is u1 v j1. Yes, and the next one, a2 j2 becomes u2 v j2. And then you can continue until the end. The last one becomes un v jn. Yes. But what can I write? I can write this is equal to u1 times u2 up to un, and then I can write vj1 vj2 up to vjn. Yes, and then I can write it as u1 u2 up to un. What is happening here? I am not completely sure right now that vj1 is v1 or vj2 is v2, but I know that j1, j2, jn is a permutation of 1, 2, and 3 up to n. So exactly one of these factors is v1. Which one I don't know. Exactly one of these factors is v2. Again, which one I don't know. And exactly one of these factors is vn. So it means that the product is definitely v1, v2 up to vn. The product of these things. So it means that you see any typical elementary product, any generic elementary product that I choose from this matrix, it's always equal to this, the product of all components of the first vector multiplied by the components, all components of the second vector. So it means that all of them, all elementary products are exactly actually the same. One interesting point about this problem is this. So here we prove that all these elementary products are equal to each other. So if we are interested in calculating the determinant, you can pull this expression, which is common to all of them, out, so it becomes u1 up to un multiplied by v1 v2 up to vn. Then you have a sum of a bunch of ones or minus ones, yes, j2 up to jn. So if I am interested in calculating the determinant, of course this is not demanded in the problem, but this becomes this. And this sum is over a bunch of positive ones or negative ones, because this is a sign of a permutation. If the permutation is even, this turns out to be positive 1, and if the permutation is odd, it turns out to be negative 1. So we are adding over a bunch of positive and negative ones. But there's also a theorem in abstract algebra that proves that the number of odd permutations is exactly equal to the number of even permutations. So it means that we have the same number of positive ones in this sum as we have the negative ones. So it means that this sum, if you know that fact, is always equal to 0. So this means that the determinant of A is equal to 0. So it's very interesting. It means that if you choose two vectors from Rn, two column vectors from Rn, no matter which components you choose, what are the numbers that you choose as components, if you set up a matrix by multiplying one of them by the transpose of the other one, you end up with the square matrix, and the determinant of that square matrix, independent of how you construct these vectors u and v, is always 0. Okay, so that, I think this is also worth to know about it. Okay, so until the next video, be safe and goodbye.